Alright, hey guys, what's going on? So today we're going to be going over some more general relativity. As you've also noticed, I decided to delete the biophysics playlist, and I'm going to restart it because I didn't really like how it was starting. And so keep an eye out for different type of biophysics lessons that are going to be coming out soon. Anyways, in today's discussion, we're going to be talking about constant linear acceleration within the framework of special relativity. This is going to be the last topic we talk about in special relativity because I really want to dive in to general relativity. We're also going to kind of look at something called the ADM formalism. We're going to briefly talk about it in this video just because I think this video is going to be a good little bit of a segue into that. And that is going to be a little bit of a segue into quantum gravity, which is also something I want to get to, either in this playlist or in a separate playlist. But in order to get into quantum gravity, we really have to have general relativity under our belt. But in order to have general relativity under our belt, we want to be motivated into wanting to understand general relativity. And I believe that one of the primary key motivations in understanding general relativity is the desire to understand quantum gravity. To me, quantum gravity has always been something of an interesting purview of science to investigate. As someone being in biophysics, it seems to be somewhat relevant to me because I study protein dynamics, and proteins are made up of particles, and particles obey the laws of quantum physics, but proteins are also subject to the laws of gravitation, right? They're massive enough to the point where they can feel gravitational forces. For example, gravitational flow cytometry is a method that completely relies on the concept of gravity to elute proteins out of some sort of fractional tube. But anyways, I digress. Let's talk about constant linear acceleration, and we're gonna look a little bit at quantum gravity here, or at least the beginnings of quantum gravity. Okay, so when we're talking about constant linear acceleration, again, I apologize for the dog barking in the background. We are interested in looking at a couple of things here. One is going to be the velocity of an object. The other one's going to be the acceleration of an object. The velocity, again, is the derivative of spatial components, and the acceleration is the double derivative of spatial components, or the derivative of the velocity, right? So in this case, that's these two statements right here. Therefore, this is the double derivative of the spatial parameterization or components of some object, okay? We're going to talk about this in more detail. But anyways, okay, so if we take a velocity vector, we inner product it with itself, it's going to be 1, right? The inner product of some vector with itself is 1. Okay, so we can take the derivative of that, and we can say that the derivative of the inner product is 0, because the derivative of 1 is just 0. And when we do that, we get the derivative of the velocity with respect to some parameter, and the derivative of the velocity with respect to some parameter. Well, that's just acceleration, right? So these two guys, acceleration, velocity, acceleration, they're not, these two guys are the same. So we can multiply them by 2, we can divide both sides by 2, and we get this relationship. So this relationship here tells us that the acceleration of an object is perpendicular to the velocity of an object, okay? And so, again, this all comes from the fact, this fact right here. And so, suppose we had a particle, right? So this little green guy is our particle. This green guy is our particle, and it's traveling along some curve. It can be a geodesic. We'll talk about geodesics in later videos. But this particle can travel along some curve, and it has a velocity, right? Its velocity is given by, again, the derivative of a curve is a line that's tangent to that curve that represents the rate at which something is traveling along that curve. And then the acceleration, as we just saw, is orthogonal to the 4 velocity. Okay? These two guys, we're thinking of them now as 4 vectors, just like we thought of 4 vectors living in Minkowski spacetime. These 4 vectors, again, are, they have their temporal component and they have the 3 spatial components. And so when we see this here, we say that if this lives in the tangent space, if V lives in the tangent space, it's said to be time-like. If it lives in A, since it's perpendicular to V, it's said to be space-like. And that's the relationship between these two vectors. One's space-like, one's time-like. And A mu, therefore, when we get an inner product, when we take an inner product of it with itself, we get, again, some number. We're going to call that number A squared for right now, okay? Because it's not, for reasons beyond what we're going to be talking about in a review on special relativity, this is going to be the acceleration of an object, okay? And so the acceleration is squared, right? And the reason we define it as this is because when we do this guy, we have our temporal component minus our spatial component, right? So this is an inner product, that's this, and we're saying that that's all equal to an acceleration. And so the components of the object at some position are hyperbolic in nature, because this is a hyperbolic equation, right? I'm skipping over a bunch of stuff because I think I want to get into the general relativity of things, not to the special relativity. And I will go into special relativity in a separate playlist again. Again, the idea here is that the space-like vectors, the inner product is going to look something like this, right? So this could be 1, right? It could be 1, it could be 2, it could be 3, it could be 4. That's all, this is the relationship we're looking at, though. And so, when we're looking at this from a light cone perspective, we can think of this as the light cone. So objects can't travel faster than the speed of light, right? So the velocity vector lives inside the light cone. The acceleration lives on the space-like plane that is perpendicular, right? Because we just said it was orthogonal or perpendicular to our time-like vector. And so we can actually, this is really just a bunch of algebraic manipulations here, but the point here is that this is the spatial components and the temporal components are related to each other by this A factor, okay? If we plug these guys in, these hyperbolic relationships in, to this equation, we get this, and then we can get, from there we get to here, right? We flesh the square out, and then fleshing things out even more, we get this, and then we get, right, so I'm multiplying, let's see, what am I doing here? So right, so this times this is this. This times this is this. And then this, and then these two ones right here, this -1, this -1, well, that's going to be plus, and we get the factor of 2 out front. Okay, so that's when we add this guy. That's when we add it, right? So this can be this guy times this guy times this, and so we add them. That's where we get that 2. And then we can multiply everything out by A squared. And then we get this. So right off the bat, notice how the A squared doesn't really matter that much. It can be 1, okay? It doesn't matter though, right? It all falls out in the end when we find out the relationship between A and V. So we don't really actually have to specify A in order to understand that this is the solution. This is what we get here. A could be 1. It could be anything, but we don't. A doesn't really play a role in understanding how this is all hyperbolic, right? When we say this, everything checks out, okay? And we can find out that it's hyperbolic through this relationship. The forward acceleration of an object is therefore orthogonal to the forward velocity space-like. It's been shown that the position components are hyperbolic, and that's this relationship right here. That's why I have a 3 right here. And so we get we can get this relationship as well. We just do some algebraic manipulations, and we get to this point where x1 is related to x0. Again, all keeping in mind that x1 is the same thing as the spatial component, and x0 is the same thing as the temporal component. Okay? So this is the restriction, right? This is the restriction that we have. Right? So if we're given the component, the temporal component, we can actually calculate the spatial component. That's the power of special relativity, right? The power of special relativity isn't to say, well, 4 vectors exist and that's all that exists. The power of special relativity is 4 vectors exist, but there's a very tight relationship between the spatial and the temporal components. And that really tight relationship is crucial. It's hyperbolic in nature. Okay? And so we can take the derivative also with respect. We could take the derivative of the spatial components with respect to the temporal component. Like this is saying something like dx dt, right? Right? Because we said dx0 was similar to dt, or was the same thing as dt. So we take the derivative of this, we get this, and this is all, if again recalling from calculus, we get this. Eventually we get to this point. Then we can take the double derivative, which is to say that we're taking the derivative of this guy. And again, so this is a product rule, and then chain rule in here, right? So product rule, we get this, plus the chain rule for this guy, we get this. And then here, so this stays the same. We flesh out the denominator here, and we cancel out our 2's. And then we get, and so we get this guy. We can factor out this guy here, and we get this. To get from here to here, we need to understand this guy right here, right? So this is what we said before. X, this here is this just that squared, right? That's that squared, and then we get we can add a squared to both sides. We get this, right? And so this here is just the hyperbolic cosine. Then we take the square root. Okay, when we take the square root, we get that the square root of this, which is right here, is the cosh function, or the hyperbolic cosine. And then we get, so that's where we can replace this guy with this guy. And then we can, all of this is, well, right, this is that. And then this here is going to be this, right? This is not too difficult to see when we understand what the sine and the cosine is. Okay. And so what we get is we get is this, right? These guys will cancel, and this actually should not be a tangent, right? This should be, that's why I was messing myself up here. That should be a cosh, right? Because, cosh, because this guy is right here. And we square both sides, we get this, right? And then sine over cosine is tangent. All right, so then we get this. Okay, where A again is just that A parameter, and S is the parameterization of some curve. Okay, and so S really was this right here. We introduced S down here. And again, S was just, as you go along some curve, you need to parameterize it, right? And so that's, the S is the parameter along that curve. Okay, and so this is the relationship, the double derivative of some spatial component. Again, this is the t, dt. So dx dt is going to be this. This is a hyperbolic relationship. We have hyperbolic cosine, we have hyperbolic tangent. And so these are the restrictions that special relativity places on us. You can take a look at my early videos in my No Nonsense Quantum Field Theory playlist to also rehash on some special relativity. Okay, so we talked about all of this. Now let's get back to this picture up here. This picture up here is a picture that I really want to sort of focus on for the remainder of this playlist, or at least for the foreseeable future of this playlist, because the idea here is that, again, particles, objects, they're going to travel along geodesics. We haven't talked about geodesics yet. We're going to, but again, the idea is that, well, nothing can travel faster than the speed of light, so everything has to stay within that light cone. Okay, the acceleration, however, is going to be perpendicular, and it's going to sit within that the hyperbolic this plane, this plane of there's different names to this plane, but this is the acceleration. This is the acceleration. This here is the velocity vector. Velocity is the tangent vector. Acceleration is orthogonal to the velocity. And this is going to be the picture, right? And I mentioned talking about quantum gravity for a little bit in this video. And so here's how I want to do that. Suppose we had a manifold. Let's do this in black. Here's our manifold. And our manifold has components on it. And suppose these lines represent geodesics that a particle is traveling within the manifold. Now, suppose now we have our light cones. Our light cone, we can have a light cone existing at every point in space-time, each having a different orientation, if you will. Something like this. And suppose now we take another manifold. This time the lines look a little bit different. We have our light cones again. I'll just draw two of them for right now. And a particle is traveling along a geodesic from here to here. Right? And the geodesic keeps on going in different directions. Well, let's actually draw this a little bit better. Particles can't travel faster than the speed of light. So it has to go through the light cones. Like that. Alright. This difference in here. This is a temporal distance. Okay, this is just two changes in time. So from time 1 to time 2, this is how we're picturing the evolution of these manifolds. The manifolds themselves can change. And when the manifolds themselves change, the light cones can change different orientations. And when the light cones change different orientations, well, this is called the foliation in the manifold. This foliation in the manifold means that we're taking just the temporal components of the manifold and layering them on top of each other and having the height difference between each one being equal to the temporal distance between the two. This is a way. One of the big things that we're going to want to understand when we start talking about quantum gravity, because when we do that, we now have this picture of a dynamic metric, a metric that can change in time, okay? And the dynamic metric, if something's changing in time, think about this for a second, if something's changing in time, we can describe its change in time through a differential equation, okay? Where do differential equations come from when we're talking about modern physics? Lagrangians. So if we can develop a Lagrangian for our system, whatever system we're talking about, if we can develop a Lagrangian, we should be able to get the laws of motion from that Lagrangian. Okay? Well, if we have a Lagrangian, then we should have a Hamiltonian. Okay, and if we have a Hamiltonian, then that is the gateway into a Hamiltonian formalism for GR. Okay, the Hamiltonian formalism for GR then puts us into the purview of quantum speak, right? The quantum mechanics, quantum field theory. Okay, the idea here is that when we foliate space-time, we foliate it into a spatial and temporal component. We can get how the metric changes with respect to time. And we get how the metric changes with respect to time. Then we can understand how we might be able to get the laws of motion, the differential equations. And when we get the differential equations, we can start understanding the Lagrangians. When we start understanding Lagrangians, we can get Hamiltonians. When we get Hamiltonians, then things become quantum, because then we can take Heisenberg uncertainty principles, we can find energies and all this stuff associated with that kind of stuff. And so this is, I do want to sort of entertain the idea of doing quantum GR in this. And we're going to, right? It's going to take a while to get there because we need to solidify some concepts on the way. But we're going to get there. And with that being said, I hope you guys enjoy this kind of content. Make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.